This is the morning review of Chapter 3, Curve Sketching and Optimization. Let's look at some definitions here, or review some definitions here. First off, extreme value theorem. So here's the graph that represents extreme value theorem, where we're trying to identify the absolute max and absolute min values on the closed interval. So if a function is continuous, that means no breaks in the graph, on the closed interval, meaning that the endpoints are defined on the closed interval from a to b, then f of x has both an absolute max and absolute minimum value on the closed interval ab. So what we need to do is, if we wanted to identify the absolute max and absolute min, we're guaranteed that if it's closed interval and continuous, that absolute max, absolute min will exist somewhere on this graph. So we have to be able to identify the endpoints and also identify the critical points. And after we identify those points, we plug them all into the original function and compare the y values. Whatever the highest y value is will be the absolute max. Lowest y value will be the absolute min. Just be careful that to find critical points, we need to set our derivative equal to 0. So if the derivative function has both a numerator and denominator variables, then we set numerator equal to 0 as well as the denominator equal to 0, simply because if the derivative is undefined, then it could be a sharp point that could also still be a candidate for an absolute max or absolute min. So any critical point that sits in the denominator of the derivative also needs to be considered as a potential absolute max or absolute min. All right, mean value theorem. So it says here that let a function be continuous on the closed interval and differentiable on the open interval. So we have a function that's where there's no break in the graph, as well as the fact that the slope is defined at every point on the graph. Then there is at least one point on the open interval where f prime is equal to f of b minus f of a over b minus a. So this is talking about, this represents the slope of the secant line. So the slope of the secant line, the slope between the endpoints, will be, there's a guarantee that whatever the slope of this secant line is, there will be at least another point on the curve between the two endpoints where there's a slope of the tangent line that matches exactly with the slope of the secant line. So to find that c value, we set the derivative equal to the slope of the secant line. All right, Rolle's theorem is a subset of mean value theorem, but there's one more condition. So not only does the function need to be continuous on the closed, differentiable on the open, but the endpoints have to have the same y value. So we need to test a and b in the original function and make sure they have the same y value, because if they do, then Rolle's theorem applies, which is now going to not only guarantee the slope of the tangent line matching the slope of the secant line, but the slope of the secant line in this case will be 0. So we can guarantee a slope of 0 as tangent line, so we can guarantee that there's going to be a relative max or relative min somewhere between the endpoints. All right, number one, we have a function here on the closed interval. Determine the max and minimum values. So this is, we want to first confirm that the conditions are there to apply extreme value theorem. So we need to determine whether the function is continuous on the closed interval. It doesn't have to be differentiable, it just has to be continuous. So continuous means that there are no breaks in the graph. Breaks in the graph we can identify by looking at the denominator. If there's any point in the denominator that will cause the denominator to be undefined, then we know there's a break in the graph. In this case, though, if we try to set x squared plus 1 equal to 0, we can we'll never be able to find an x value, a real number, that fulfills that condition. So we know that even though there's a variable in the denominator, there's no x value that will cause the denominator to be 0. So we know the function will be continuous everywhere. So we know extreme value theorem will apply. All right, so we need to identify some critical points, because not only do we need to test endpoints, we need to identify and test critical points. So to find critical points, we need to find the derivative. So to find the derivative, we can go through Quotient Rule. So f prime g minus f g prime all over g squared. So f prime, the derivative for 2x becomes 2. The derivative for x squared plus 1, f prime times g, the original g function stays as x squared plus 1, minus f, so 2x stays 2x, and then the denominator f prime g minus f g prime, so g prime, the derivative for x squared plus 1 becomes 2x, all over denominator squared, all over x squared plus 1 quantity squared. If we distribute the numerator through, combine like terms, we can now have our derivative function, which we can set equal to 0 and find our critical point. Notice again, the denominator will not produce any critical points. There's no x value that will cause the denominator to be 0, but the numerator we can set equal to 0. So if we set the numerator equal to 0, if we can clean this up a slightly bit more, we get 2 minus 2x squared. Set that equal to 0, we get x is equal to plus or minus 1. So we have now 2 critical points as well as 2 endpoints to test. Another thing to keep in mind is when you find your critical points, make sure your critical points sit between your endpoints. If you have critical points that sit outside the endpoints, then that's outside of our domain that we need to test. So we have to make sure that just because you get a critical point doesn't mean that it'll be a point that we need to use. But in this case, 1 and negative 1 falls between negative 2 and 2. So we're going to test all 4 points, the endpoints as well as the critical points, plug them all back into the original function, and then compare their y values. Whatever has the highest y value will be the absolute min. Highest y value will be absolute max. Lowest y value will be the absolute min. So in this case, absolute max is going to be y value of 1, and then absolute minimum will be a y value of negative 1. All right, number 2, determine if Rolle's theorem is satisfied. So Rolle's theorem, remember, is a subset of mean value theorem, but with the third condition, not only continuous, differentiable, but also endpoints have to have the same y value. So let's make sure that the function is continuous and differentiable. Notice that if we were to expand all this out, it'll just end up being a polynomial. So if we're dealing with a polynomial, no breaks in the graph, and we know it will always be not only continuous but differentiable. So we can just go ahead and state that. Just by looking at this equation, we know that there's not going to be any issues with continuity or differentiability. So we can say that function is continuous on the closed interval, differentiable on the open interval. Now, first 2 conditions are met. We need a third condition to also be met if we want to continue with Rolle's theorem. So the endpoints, we need to plug them back into the original function and confirm that the endpoints produce the same y value. So negative 2 plugs into the function, and we get negative 1 times 0, which is 0. If we plug 3 into the function, we also get 0. So they both produce 0. Now, just to make sure that we understand, these do not have to be 0. They just have to have the same y value. But I think a lot of homework problems that you see, as well as examples, have y values being both 0. So just to confirm and make sure, these could be 5, both 5s, or they could be both be negative 8. As long as we have the same y value, Rolle's theorem will apply, assuming the first 2 conditions have already passed. Okay, so now we can guarantee that somewhere between the endpoints, there's going to be a slope of the tangent line that is going to be exactly 0. So what we need to do is we need to find the derivative and set that equal to 0, and then solve for x. So to find the derivative, I can see that I can apply product and chain rule. So product rule, f prime g plus f g prime. So the g prime is the derivative of x plus 2 quantity squared, which is bring down the 2, keep the parentheses, subtract 1 from the exponent. Now at this point, rather than expanding everything out, I'm looking for a shortcut here where I can just factor from this point rather than having to expand everything through. So if I look at the 2 expressions on either side of the plus sign, I see that there's a common factor of x plus 2. So if I take an x plus 2 out from both terms and combine the remaining, what's available, or what's remaining, I'm left with x plus 2, and then this expression gives me 2x minus 3, and if I continue to clean that up, I get 3x minus 4. Now I have my derivative that's in factored form. I can now find the critical points, which is at negative 2 and 4/3. All right, so we have 2 points where the slope is 0. However, we have to consider that we only care about our C value that sits between the endpoints. So anything that is on the endpoint or outside, we have to eliminate. We're only guaranteeing at least 1 point C on the open interval. So you have to be careful. Even though -2 is sitting right on the endpoint, we have to eliminate that. Only 4/3 is acceptable. All right, number 3, determine if mean value theorem is satisfied for our function on the closed interval. So mean value theorem are only 2 conditions: continuity and differentiability. Then we can guarantee that there's a slope of the tangent line that matches the slope of the secant line. All right, so if we look at this function, this is essentially a polynomial. If we distribute the x through, polynomial functions will always be continuous and differentiable. So we just have to look at that and then just state that out. There's no need to do any further tests. So now we need to find the slope of the secant line. So slope of the secant line, because our conditions, our 2 conditions have been met. So now we can jump directly to what can be guaranteed with the mean value theorem. So we need to find the slope of the secant line. So to do that, we need to first identify some order pairs for us to plug in. So we're going to plug -1 into the original function, plug 1 into the original function, and my order pairs will be -1, 0, and 1, -2. I'm going to find the slope of the secant line, which I'm going to call average slope. So change in y over change in x, -2 minus 0 over 1 minus -1, which is -2 over 2, which is -1. So now we're trying to guarantee an x value where the slope of the tangent line matches this particular slope of -1. So we set -1 equal to the derivative. So to find the derivative, we can go through power rule. I could go through product rule, but if I just distribute this through, I can just much more easily just deal with power rule instead. All right, so x cubed becomes 3x squared, x squared becomes 2x, 2x becomes 2. I set the derivative. I want to find out when is the slope of my tangent line going to match exactly that of this average slope of -1. So I can set the derivative equal to the average slope. So 3x squared minus 2x minus 2 equals -1. Now if I have something that looks like this, I need to bring everything over to one side, set equal to 0, and then factor. So 3x squared minus 2x minus 1 is equal to 0. Continue factoring, I get 3x plus 1 times x minus 1. Solve for x, I get -1/3 and 1. Again, our c value, we're guaranteed at least 1, but any c value needs to sit on the open interval between -1 and 1. So if anything falls outside or on the endpoint, we have to eliminate. So it looks like 1 we have to eliminate because 1 is on the interval. We only care about a c value that sits between. So c, in this case, -1/3. Hey, number 4, the graph of the derivative is given. Sketch a possible graph of h of x. All right, just as a reminder here, if we're looking at the derivative graph, we have to make a slight adjustment in terms of what we're looking at. We have to identify the fact that this y-axis no longer represents physical points on the graph, on the original graph. The y-axis now represents the slope of the tangent line at any point on the original graph. So I'm going to make a reminder here. Anything above the x-axis is going to be where the original graph has a positive slope. Any parts of the graph that we see below the x-axis represents where the slope of the original graph is negative. So let's identify some critical points, as well as and also any points that sit on the x-axis will represent where the slope of the original graph is equal to 0. So let's find our critical points first. Our critical points will be where the slope is, where the x-intercepts are. So 1. Here I'm going to just make my best estimate as 2.8, so more than 2.5 but less than 3. But that's open to interpretation, so that's not going to be, we're not going to be able to know exactly what that point is, but I'm just going to call that 2.8. Here, this is slightly between 5 and 6, so I'm going to call this 5.7. Okay. All right. Also, so now if I create my slope sign line, I can just look at the behavior of the slope or the behavior of the order pairs on either side of the x-axis. So to the left of 1, all these points are below the x-axis, so that tells us that the original graph has a negative slope. So I'm going to provide this arrow symbol to indicate, give me a visual as to what the original graph looks like. Okay, to the right of 1, we see the graph is sitting above the x-axis, so positive slope. Between 2.8 and 5.7, this portion of the graph is below the x-axis, so that represents where the slope is negative. And then to the right of 5.7, it's going to come up above the x-axis, so we're going to say that's a positive slope. All right, we're going to create sign lines for f double prime. So if we're looking at the f prime graph, any peaks and valleys will be points of inflections, okay? Because these are going to be the points where the maximum slope or the minimum slope, steepness, okay, has been reached. So my POI here is at 2 and at 4, okay, x values of 2 and 4. And then if we look at the behavior of the slope of the f prime graph, that will indicate when the graph is concave up or concave down. So here in this case, this portion has a positive slope, so that's concave up. This is concave down, and then concave up to 3, or up to 5. Let's see, 1, 2, 3, 6. Sorry, 6. And then here, this is neither a positive slope nor a negative slope. This is just going to be a slope of 1, so we can make that adjustment on the graph as well. So I'm just going to draw a rough sketch here. We know we want a relative min at 1, so I'll just choose a point below the x-axis. 2.8 will be a relative max. 5.7 is going to be a relative min. And then from there, I'm going to just connect the points. Also knowing that somewhere at x value of 2, I want there to be a change in concavity. Somewhere at 4 to be a change in concavity. And then to the right of 6, I want the slope to be exactly 1. So we see that this is a y value of 1. So I'm just going to best represent a slope of 1 for the original graph. So concave up to POI, concave down to the second POI, concave up, and then just a linear graph with a slope of 1.